Hello and welcome to mathsplus. Today we're covering the Leaving Cert Higher Level 2022 question 3 in the complex numbers. So first of all, we just have a straightforward multiplication question, and we have z is equal to 6 plus 2i. Now we need to get z minus I by z, and we have the result. So let's get the result and compare. So we have 6 plus 2i minus I by 6 plus 2i. Let's multiply out our brackets. So we'll have minus 6i minus 2i squared. So for the complex number I, we can state that I is equal to the square root of negative 1, and I squared is equal to negative 1. So now we will replace this I squared with negative 1. So for the result will be 6 plus 2i minus 6i minus 2 brackets minus 2. Now we're going to get a real value over here. And let's look at what we have. So we have 6 for the real and 2 for the real. So overall we have an 8. And secondly, we have a plus 2 and a negative 6 for the I. So this will give us a result of minus 4i, which is correct. So let's look at the second part. In the second part, we have to add 2 modulus on the left hand side and get the modulus of the difference of z and iz, just like the one in the first part. So let's state everything out to have it on together. So z is equal to 6 plus 2i, iz is equal to minus 2 plus 6i. Okay, so where did I get that from? Well, remember, if I get I by 6 plus 2i, I will get 6i plus 2 by I squared, which is negative 1. So that'll give me minus 2 plus 6i. Okay, so let's look at the rest. And remember, from the first part we have z minus iz, and that was equal to 8 minus 4i. So the modulus over here is basically the coefficients of the real and the imaginary squared. Put a square root over it as we want to get the distance from the origin. So let's put it all together. So z squared, the modulus of z squared will be 6 squared plus 2 squared. Okay, put your square root on all that. And also we have a square up here, so we're going to bring that into it. See this square here, we're going to bring that into it. So let's write it in for now. And the second part now is iz squared. So we have that above, and we have minus 2 for the real, and we have plus 6 squared. So let's put all that in the square root again for the modulus. Okay, so we have this side completed now. Okay, on the other side, let's apply the modulus again. So we put the square root, and then we put the inputs of the real squared, the imaginary part, so 8 squared plus minus 4 squared, and we're going to square that up again. As you can see, there's a square on the right hand side. So let's see what we get, and is it going to work out? So 6 squared plus 2 squared is 36 plus 4, and if I square root and I square at the same time, it will be a cancellation because they're two opposite functions. So again, you can remove the square root, and over here again we will get 4 plus 36. Okay, and over here we have 64 plus 16. So on the left hand side we will have a sum total of 40 plus 40, 42 moduli, and 80 over here. And 80 is equal to 80, therefore this is true. Okay, so let's go on to the next part. So I just want to read this now for a moment. So we have a circle which goes through the coordinates of the original complex number z, and then it goes through iz, and also it goes through the origin. So it looks very complicated at the moment because we have to apply some geometry and get the area of circle C in terms of pi. So if we're getting the area, we need the radius. So if we look at where the radius is, it's half the distance between iz and z. Alright, so we could use the midpoint formula here and get that center coordinate. Well, that wouldn't really help much because then even if we got the modulus, then it would be the link to the origin. So let's look at an overview, because if we have z squared and we also have iz squared over here, we could say that they're going to be the hypotenuse squared. But remember, we already have that solved because we know that z squared plus I squared modulus is equal to the z minus I squared modulus. So that means we already have the hypotenuse worked out, as you can see. This is true. So we apply the Pythagoras Theorem, and this will ensure that we get the modulus. So let's look at the geometry now, as if you observe that, then it will make sense. So we can say that the z minus iz is actually the diameter, which is 2r. So now we can say that 2r squared is equal to the modulus of z minus iz squared, and we know that that is 80 from the previous section. All we need to do now is solve for r and use the area formula. So we can get r squared by 4 is equal to 80. And the rule I use there is a to the power of n is applied to both values inside here, so don't forget to do that. So if we have a to the power of n and then we have m outside, we can multiply in our power, but it applies to both the 2 and the 4. So let's divide across. So r squared is equal to 80 over 4, which is 20, and we can leave it like that for now, because remember, we want to get the area, and the area is equal to pi r squared. So pi by 20, or we could write it in here as 20 pi. So it looked very complicated at the start, so we gotta deduct and pay attention to the previous parts, because we already had a lot of the workings already done. We just have to spot that the rule we just proved was related to the geometry. Alright, so part B now is the final part of the Leaving Cert 2022 Complex Numbers question 3 paper. So let's look at the rectangular form. So rectangular form is a plus bi. And if we apply a power to that, we could use the Moivres theorem. And down here, you can see with the Moivres theorem, z is equal to r cos theta plus I sin theta. If we apply a power in, then we can bring the in with the r, and which is the modulus, the length from the origin, and also the angle, and that's called the argument. So for this rule, we need the polar form. Okay, so that means we need to get r and we need to get theta. So let's get the polar form before we apply the modulus. So we need r. So remember, a plus bi is equal to r cos theta plus I sin theta. As we have r cos theta is the adjacent and r sin theta in the other direction is the opposite. So r is equal to the modulus of root 3 minus I. And if we look at that in polar form or rectangular form, a is equal to root 3 and b is equal to -1. So let's get the modulus. So r is equal to the square root of root 3 squared plus -1 all to be squared. Therefore r is equal to 2. So we have the first part of the polar form already worked out. So as you can see now, we need to get to theta, and we need to find out where it is first of all. So if we plot it, you can see on the diagram the coordinate is in the 4th quadrant. Okay, so first of all now we're going to get our reference angle, and our reference angle is going to be related to the a and b, which is going to be off our x and y axis. So let's look at that. So if I get tan of theta is equal to opposite over adjacent, which is b over a, and I can say theta is equal to inverse tan of b over a, and we can substitute in now. So I'm going to call this our reference angle because it's not completed yet. So the tan inverse of b is -1. So I'm going to place 1 in there and root 3 in there because I just want to get the reference angle and I want to get in the first quadrant. So theta is equal to 30 degrees. So we can leave it in degrees here because we're just computing it out. We do not need radians because it would make it more complicated. We'd have to set our calculator to radians. So let's use degrees for a simple approach. So now we just need to get our theta argument. So theta argument is equal to, so we want to get this angle. So let's look at the diagram and let's see where it's at. So if we go from the x-axis here and we go all the way around anti-clockwise until we reach the actual line which would join the origin to the coordinate, we would get 330 degrees. We have 30 in here, which is our reference angle. So our actual angle is 330. So always use the diagram and it will work out. Alright, so all we have to do now is put it all together and compute it out with the calculator. So a plus bi to the power of 9, which is root 3 minus 1 to the power of 9, and that's equal to r, which is 2, by cos of 330 degrees plus I sine of 330 degrees, and that's all to the power of 9. So now we're going to bring in our 9, as you can see below. Again, we're going to bring in that 9, okay, it replaces the in, and we're going to bring it in here and bring it in here. So it's going to compound our angle as a power, and then it's going to multiply our angle. So we have 2 to the power of 9 by cos of 9 by 333. 330 degrees plus I sine of 9 by 330 degrees. So let's work all of that out in our calculator. Let's go Z9 here. And that will give us 2 to the power of 9 is 512. Cos of 9 by 330 will give 0. And sine of 9 by 330 in degrees again be I by, and that will give a 1. So our result 512 by 0 is going to be 0. That's for our real. And 512 by our I is 512i. That's our imaginary, which is our B. So 0 for A and 512 for B. So I hope you enjoyed that solution. And as always, thank you so much for watching mathsplus. And keep an eye out for the next video, as it will be coming shortly.